This $45 device runs on nothing but bacteria and wet dirt. It needs no solar panel, no lithium battery, and no fuel to burn. Yet it generates a continuous electric current, day and night, powered by microbes that were already living in the ground beneath your feet. The organisms doing the work were first shown to make electricity in 1911. The device has been sold as a science kit for years, and still, it does not appear on a single federal energy incentive list. It's called a soil microbial fuel cell. It runs on rot on the slow breakdown of organic matter in the soil, and it does not stop when the sun goes down. By the end of this video, you'll know exactly what it is, how the electricity is made, and how to build one yourself for the price of lunch. Let's dive in. Consider how many small electronic sensors the modern world is starting to bury. Soil probes on farms, moisture monitors under roads and bridges, trackers in forests and along pipelines. The number is already in the billions, and the engineers building these networks talk openly about a future with trillions of them. Every one of those devices needs power, and almost every one of them gets it from a battery. That is the problem nobody in the brochure wants to sit with. A battery is a finite object. It holds a fixed charge, it drains, and then someone has to dig it up and replace it. Do that across a handful of sensors, and it is an afternoon. Do it across a million, and it becomes a permanent, grinding maintenance operation with no end date. Then there is what the batteries are made of. Lithium cells are packed with toxic, flammable chemicals and rare metals pulled through long, conflict-ridden supply chains. When they are discarded, and at this scale, they are discarded constantly, those chemicals leach into the very ground the sensors were meant to protect. You are contaminating the soil in order to measure it. Solar does not rescue you here either. A panel buried under dirt sees no light. A panel in shade or under a canopy produces almost nothing, and every panel on Earth stops the moment the sun goes down. For a device that has to run continuously, underground, for years, a solar cell is a part-time worker. So this is the real situation. We are about to scatter trillions of tiny machines across the planet, and our plan for powering them is a toxic, finite cell that dies and has to be replaced. That is not a power source. That is a subscription you pay in labor and buried metal. And the strange part is that a permanent alternative was sitting directly under every one of those sensors the whole time. The dirt under your feet is not inert, it is breathing, and breathing makes current. Ordinary soil is packed with living microorganisms, billions of them in a single handful, present in virtually every patch of ground, sediment, and stream bed on the planet. Among them is a particular class of bacteria that does something strange. Instead of breathing oxygen the way you do, these microbes breathe metal. As they feed on the decaying organic matter around them, they strip electrons from it and hand those electrons off to metal compounds in the soil, like the rust on a buried nail. That transfer is an electric current. It is happening right now, in the ground outside, whether anyone is measuring it or not. This is what separates a microbial cell from an ordinary battery. A battery is a sealed object with a fixed charge that runs down. This runs on decomposition, on rot, the same slow breakdown happening in any compost heap. Nothing is manufactured, nothing sits on a shelf waiting to die. As long as there is organic matter and moisture, the microbes keep eating and the electrons keep flowing. No cell to replace, no fuel to buy, no monthly invoice to anyone. But that raises the obvious question. Bacteria are microscopic. How could something you cannot even see produce a current you could actually capture and use? A microbial fuel cell is, at its core, a battery, an anode, a cathode, and an electrolyte between them. The only difference is that here the electrolyte is alive. Start with the anode, the negative electrode. In a soil cell, it is usually a piece of carbon felt or graphite cloth buried down in the wet, oxygen-starved dirt. This is where the electricity-generating bacteria set up shop. Species like Geobacter and Shewanella, the metal breathers, colonize the surface of that electrode, forming a thin living skin called a biofilm. As they consume the organic matter around them, they need somewhere to dump the electrons they strip loose. So they pass those electrons directly onto the carbon, through proteins on their outer membrane and through tiny conductive filaments some of them grow, often called nanowires. Now those electrons are sitting on the anode with nowhere to go. Run a wire from that anode up to a second electrode, the cathode resting at the surface where there is oxygen, and the electrons flow. They travel up the wire, reach the cathode, and combine with oxygen and protons from the soil to form plain water. That flow through the wire is your usable current. And here is the part that separates it from solar entirely. The reaction does not need sunlight. It runs on the microbe's own metabolism, which means it runs in daylight, in darkness, in fog, and underground. In the words of the Northwestern engineer who led the most recent research into these cells, as long as there is organic carbon in the soil for the microbes to break down, the fuel cell can potentially last forever. There is a catch, and honesty about it matters. A single cell produces very little, a few tenths of a volt and microwatts of power, not the punch of a AA battery. But power scales with electrode surface area, and cells can be wired together, one to the next. Raw output this small also has to be stepped up before it can do real work, and we will get to exactly how. First, though, you should know that none of this is new. The first working version predates the light bulb in most American homes. In 1911, a botanist named Michael Cressey Potter, working at the University of Durham in England, set out to study how microorganisms break down organic matter. What he found instead changed nothing at the time and everything a century later. As his cultures of ordinary brewer's yeast decomposed their food, they produced a measurable electric current. Potter wired up electrodes, captured the voltage, and published his results in the Proceedings of the Royal Society under a title as plain as the finding was strange: Electrical Effects Accompanying the Decomposition of Organic Compounds. He had built the first microbial fuel cell in history, and almost no one cared. The idea sat nearly untouched for 20 years. Then, in 1931, a bacteriologist named Barnett Cohen returned to it. Cohen took Potter's design and did the obvious thing nobody had bothered to do. He wired multiple cells together in series. Stacked that way, his bacterial cells generated close to 35 volts. The current was tiny, only about 2 milliamps, but the principle was proven at scale. Living microbes, wired in a chain, could push real voltage. And then, once again, the science went quiet for decades. Microbial cells became a laboratory curiosity, a party trick with no obvious use. It was not until the 1980s that two researchers at King's College London, M.J. Allen and H. Peter Bonetto, pulled the idea back off the shelf and began systematically improving the design, treating it as a serious power technology rather than a novelty. The missing piece arrived in 1987. A microbiologist named Derek Lovely identified a specific organism, Geobacter, and showed exactly how it did the job: a true metal-breathing bacterium that transfers electrons straight onto solid surfaces as it feeds. Suddenly, the mechanism had a name and a face. Researchers knew which microbes to look for and how they worked. That knowledge led to real machines. Engineers began building benthic, or sediment, fuel cells, planting electrodes directly into the muck at the bottom of rivers and seabeds, where decomposition is constant. Experimental buoys have been powered this way on the Potomac River, drawing current from riverbed mud to run instruments and transmit data, with no battery aboard at all. The science was never wrong. For over 100 years, the world simply was not listening. And then, in 2024, a top American research university finally made it reliable. In January of 2024, a team led by Northwestern University alumnus Bill Yen published a peer-reviewed study in the Proceedings of the Association for Computing Machinery, and it moved the soil cell from curiosity to working tool. The device was about the size of a paperback book. What made it work where a century of predecessors had failed was not exotic chemistry, it was geometry. Every earlier soil cell ran into the same wall. Buried too deep, the cathode had no oxygen. Left too shallow, everything dried out. Yen's team spent 2 years on the problem and solved it by turning the design on its side. They laid the carbon anode flat and horizontal, deep in the wet soil where the bacteria thrive, and stood the cathode up vertically, rising to the surface. That way, the top of the cathode always breathes air, while its base stays hydrated in the moist ground below. They even waterproofed part of it so the cell could survive a flood and dry out slowly afterward, instead of drowning. The numbers are the reason this matters. On average, the cell generated 68 times more power than its sensors actually needed to run. It outlasted comparable technologies by 120%. And it kept working across a punishing range of conditions from soil that was only 41% water by volume all the way to completely submerged. They put it to work, powering real sensors that measured soil moisture and detected touch, useful for tracking animals moving across a field, and they fitted it with a small antenna that transmitted data by reflecting existing radio signals, no power-hungry transmitter required. Every component, the researchers noted, could be bought at a local hardware store, and rather than patent it, they released all their designs, tutorials, and simulation tools to the public. The work was funded by the National Science Foundation, the USDA's Agricultural and Food Research Initiative, the Sloan Foundation, VMware Research, and 3M. This is not fringe science. It is federally funded, peer-reviewed, and openly published. Nor is Northwestern alone. One of the study's co-authors, Colleen Josephson, has been field testing soil batteries on working farms. And in the Netherlands, a project called Planty runs a related version that draws power from the ground around living plants. So, the science is proven, the plans are free, and the parts are at the hardware store, which raises an uncomfortable question. Why is a technology this well documented on precisely 0 federal incentive lists? Because the incentive lists were never built to see it. The Residential Clean Energy Credit, the most generous federal renewable incentive in American history, covered solar panels, lithium battery storage, geothermal pumps, fuel cells, and small wind turbines. Every item on that list has something in common. It is a manufactured product. It ships in a box. It is installed by a certified technician, financed through an approved lender, and metered at the point of use. Each one generates a paper trail and a stream of invoices as it moves from factory to rooftop. A jar of mud and 2 graphite electrodes generates none of that. The American electricity market runs on roughly $400 billion a year, and that revenue depends on a specific architecture, centralized generation, long transmission lines, and metered consumption you are billed for every month. A soil cell fits nowhere inside it. It produces no meter reading. It requires no service contract. It creates no financeable asset. From the perspective of that system, it is not a competitor, it is a non-entity. The practical machinery reflects that. There is no soil cell manufacturer sending lobbyists to hearings. There is no trade association. There is no underwriter's laboratories listing for a pair of electrodes buried in your garden. And without a UL listing, no building inspector will sign off on it, no insurance policy will cover it, and no appraiser will assign it $1 of value. This is not a ban. It is something quieter and more total. It is structural invisibility. And let me be clear about what this is not. Because this channel exists to cut hype, not manufacture it. No one conspired to bury the microbial fuel cell. There is no secret meeting, no suppressed patent, no villain. The frameworks that govern American energy were simply written for products that scale, ship, and bill, and a device you grow in a bucket of dirt clears none of those gates. It vanishes not because it was hidden, but because the system has no slot to file it under. Which brings us to the honest part. A soil cell is not a hidden grid killer. It will not power your house, and anyone telling you otherwise is selling something. What it produces is genuinely deliberately small. So the real question is not whether it can run your home. It cannot. The question is, what a trickle of microwatts is actually good for. Start by throwing out the assumption that power has to be large to be useful. A small LED indicator runs on microwatts. A digital clock and thermometer runs on microwatts. A soil moisture sensor draws under a single milliamp. A low-power microcontroller with a wireless link sips a few milliamps in short bursts. None of these need a wall outlet. All of them can be fed, over time, by bacteria eating dirt. And with the right circuit, a soil cell can slowly trickle charge a small battery or a supercapacitor, banking that trickle until you have enough stored to do something with it. If you want the complete build, every material, every measurement, and the wiring for scaling it up, we put together a full guide that covers everything in this video and more. The link is in the description below. Here is how the basic cell works. You need 2 electrodes made of carbon felt or graphite cloth, because carbon gives the bacteria an enormous surface to colonize. Bury the first one flat and horizontal in wet, carbon-rich ground compost. Garden soil or pond sediment works best. The darker and richer the better. Rest the second electrode at the surface, and keep it fully exposed to open air. Run a wire between them. Then feed the microbes. Mix organic matter into the soil, anything that decomposes, and keep the ground damp. The output on its own is too low to be useful directly, so you add one more part, a voltage-boosting harvester. This is a small circuit that takes the cell's few tenths of a volt and steps it up to a usable level. The kit version, the Mudwatt Hacker board, boosts the output to about 2.4 volts, enough to run a clock or blink an LED. A generic boost module from an electronics supplier does the same job for $1 or $2. For a tested starting point, the Mudwatt kit runs about $45 and includes the electrodes and the boosting circuit. You can also build one from scratch for less if you skip the board. Once your first cell is running, scale it the way the historical builders did, add electrode surface area and wire multiple cells together. One critical warning: never submerge or seal the cathode. The electrode at the surface must breathe open air, or the reaction starves and the current dies. And do not expect instant results. The bacteria need 3 to 7 days to colonize the electrode before power ramps up. This is a living system, not a battery you snap in. There are real limits, and you should know them before you dig. A soil microbial fuel cell produces microwatts, not watts. It will not run an appliance, a well pump, or a phone charger on demand. Its output depends entirely on moisture, on oxygen reaching the surface cathode, and on organic carbon in the ground for the microbes to eat. Let the soil dry out, and the current fades with it. Power builds over days, not seconds, and over long stretches the electrodes can foul, and output can drop. This is a technology for sensors and slow trickle charging, not a replacement for your grid connection or your rooftop panels. But for the price of 2 carbon electrodes and a handful of wet compost, it gives you something no lithium cell can. A power source with no fuel, no manufactured parts, and no expiration date, running on the same decomposition that happens in the ground every second of every day. The science behind it sat in a 1911 paper for over 100 years, not because it stopped working, but because it made microwatts and no monthly invoice, and the modern energy system was never built to notice something like that. If discovering the quiet, real, overlooked corners of science matters to you, subscribing and sharing is the simplest way to make sure this kind of knowledge keeps being found. We will be tracking all of it as it develops. So here's the question. If you had a patch of wet ground and $45 to spend, would you bury a pair of graphite electrodes and let bacteria run your sensors for years? Or would you still reach for a coin cell that costs less up front and dies within one? I'd genuinely like to know. Drop it in the comments.